Okay, in today's class we are going to discuss about some of the test generation methods. Please remember that we considered two problems in the last class. We talked of given a test vector, we have to find out what are the faults that this test vector covers. The other problem that we can also look at it is a dual problem, where given a fault we can find out which are the test vectors which cover such a fault. First of all, we will take the first problem, given a test vector, which are the faults covered by the test vector. A very popular method, and remember the other thing that we talked of is the fault models. Presently we are only considering the two very simple fault models, the stuck-at fault model, where we consider any of the circuit nodes to be stuck at 0 or stuck at 1. We said that under certain circumstances, many of the other faults like bridging faults or faults which there is a short and so on may also reflect as stuck at faults as some other nodes. The objective of this exercise is not to locate the fault, but only to find whether the circuit is functioning, whether it is functioning correctly or not. And the domain of discussion today is primarily combinational circuits. We are talking about how do we do testing on combinational circuits. So this parallel fault simulation is a very popular method in the industry for performing these tests or for test vector generation and then doing the tests. So in parallel fault simulation, what happens is evaluation is performed simultaneously for many faults. And the number of evaluation, we will see an example, the number of faults that can be simultaneously simulated corresponds to the word length of the host machine. So if you are talking of 16-bit machine on which this fault simulator is being run, then you can do 16 or 15 depending on if you are also doing the fault free evaluation, then 1 bit is for fault free and 15 for the faulty evaluations. So if you are working with 32-bit machines, you can do. So if you are talking of a circuit which has, let us say, we are talking of fault simulation at n nodes, we are talking of 2n faults stuck at 0 and stuck at 1 at both each of the n nodes, and then word length of the machine is w. So typically the number of runs that is required is 2n by w. That is the number of runs that would be required. That is, so many times circuit evaluations need to be performed, and we will see how it works by taking a small example. So here I have a circuit which contains 4 gates. It has 5 inputs A, B, C, D, E, and whatever I am doing right now is I am doing it at the gate level, but it is not very difficult to see that I can also replace them by more complex modules. What I really need is the input-output functionality, how the inputs and outputs are related, and I can also have more complex modules. We will discuss that point a little later. Let us just consider a gate level circuit. So the starting point is a gate level netlist. Okay, because from the netlist one can generate a circuit of this nature. So I have this circuit, so there are 5 inputs and 1 output, AND, OR, NOR and NAND gate. So given a certain input, let us say I am talking of an input which is 0, 1, 0, 1, 0. I can do an evaluation which is a fault free evaluation. So fault free evaluation would essentially be the 0, 1, 0 will evaluate to 0, this will also evaluate to 0, this will evaluate to 1 and this will evaluate to 1. So that is my, what I have shown in red is my fault free evaluation. So now if I consider the circuit with fault, let us say I consider the fault A stuck at 0. You can see that with the fault A stuck at 0, I am not going to get any difference in the evaluation of the circuit with the, because I am considering this node to be stuck at 0 and my test in vector is nothing but this to be 0. So I am not going to see any change in the circuit. So obviously all those 5 faults, this cannot simulate those 5 faults in which these primary inputs are taking the actual value, which are the stuck values. Like for example, B stuck at 1, I cannot use this test vector for doing B stuck at 1. I cannot use this test vector for doing C stuck at 0, because nothing will change, and after all I have only one output. So when can I say that I can detect a fault with this particular test vector? Only if my output I is going to be 0. Because my true value of my output is 1, the faulty value of my output has to be 0. In this case I have only one output. If I have multiple outputs, if any of the outputs change, I can detect a fault. On that particular output, I can detect the fault. In this case, I can detect the fault only if this output on this particular node, which is the I node, is 0 instead of 1. So that is not going to happen if A is stuck at 0. So I obviously, so there is nothing will happen over here. But let us say I consider A stuck at 1. If I consider A stuck at 1, again what will happen is, so this value will be 1, rest of the values will not change. So I can again not detect the fault, A stuck at 1. What I am doing is, please remember, what I am doing is I am just evaluating this circuit. I am just computing whatever operations need to be performed, and operation needs to be performed between B and C. I am doing that in the true mode and in the faulty mode. That is with the value set, the true value set, and with the faulty value set. And I can do this not just at the primary input, I can also do it, for example, as stuck at 1 here. I can do it the evaluation starting. There of course I will do the evaluation, instead of 0 I will write a 1 here, because this is stuck at 1, this is the faulty mode with F stuck at 1, and do the evaluation. So for example, this particular table shows this parallel fault simulation. So I have these nodes, I have this A, B, C, D, E, F, G, H, I, the nodes that are for each of the circuit nodes. And this is my fault free circuit, FF is my fault free, and A0 is nothing but A stuck at 0. A1 is A stuck at 1, B stuck at 0, B stuck at 1, C stuck at 0, C stuck at 1, D stuck at 0, and so on. I am considering an 8-bit machine, host machine, so I can do 8 of these faults together, 7 of these faults plus fault free evaluation together. And what do? I have the value of the node. So A stuck at 0 is 0, 0, A stuck at 1, the value of the node is 1. Input may be 0, but because A is stuck at 1, my value of the node is 1. And rest of the, of course, this A node will be same, it does not matter, B stuck at 0, A value node. B is, again I write, with B stuck at 0, this is going to be 0. For C, with C stuck at 1, this is going to be 1. With D stuck at 0, this is going to be 0 rest of the time. And E is, of course, E faults are not shown over here, they will come later. So now what do I need to do? If I consider the circuit, what is the function F? F is nothing but B dot C. So what do I have to evaluate B and C. Now once I have set up this, I can evaluate B dot C by just taking this, because in any machine that I am operating on, I can do a ANDing of the whole word. In this case it is 8-bit word, but if it is a 16-bit word, I can bit by bit I can AND the whole word. So I can actually AND this particular row with this particular row. These two rows can be ANDed together, and I can write the value over here. So when I AND these two rows together and I write the value, so basically what I am doing is I am not performing an evaluation for one fault at a time like I did when I manually tried to do this. I considered A stuck at 0 and stay. I am now doing this evaluation in parallel. I am doing it for all the faults simultaneously, which can be fitted into the word of a machine, because any machine can operate on, can perform these logical operations, Boolean operations on the whole word simultaneously, bit by bit. So I can do this as, similarly G was D or E complement, and H was F dot G complement. This is coming from that function that we had. So I am just writing I is nothing but A or H. So I can take these rows, and once I have calculated F, I can use that for calculating H. So similarly G I can calculate by taking an OR and complement of D and E, and then H I can complement by taking F and ANDing F and G and taking the complement of that, and I can. So I can do this, and once I get the result, I look at the result at this particular output I, and I know what the fault free value is. If in any of the columns, if the value under the fault is different from this, that particular fault can be detected using this test vector. My starting point was a test vector. In this case, this was my test vector. 0, 1, 0, 1, 0. This was my test vector. And of course, under the faulty conditions, whatever, if an intermediate node is faulty, for example, f stuck at 1 I am doing, I should have replaced this. If it is f1, then I should have a 1 value over here. Though the evaluated value may be 0, but I should have 1 because f is stuck at 1. And rest of the computations will be done based on that. So looking at this particular last row in this case, if any of the columns, so in this case it so happens that all these outputs are still 1 under all these faults. So the 1, 2, 3, 4, 5, 6, 7. I considered 7 faults over here. So all these 7 faults cannot be detected by this test vector 0, 1, 0, 1, 0. I can of course use another test vector and perform this simulation again and can get. So for any test vector to find out the number of faults that it covers, all the faults it covers, the number of simulations I will be required to do would be 2n by w, or actually 2n plus 1 by w, 1 for fault free and 2n for the 2n faults that you have. This is the number of evaluations of the circuit that needs to be done, and of course afterwards you have to extract where the outputs are different, and then you have to identify which the. So this complexity is important because we are talking of, as I said, we are already talking of designs which could be containing millions of gates. So obviously these numbers are important in terms of the complexity. So I just perform this evaluation. So basically what I am doing is fairly simple. I am just computing the value of the outputs given the inputs. Under simulating the fault, I am assuming that the circuit has that fault. In this case I am assuming the circuit has fault A stuck at 0. In this case I am assuming circuit has fault A stuck at 1, and so on and so on, and making a comparison between that. And it is very clear that all this testing can be done much before you fabricate the first circuit. That is very important. Everything is being done at the simulation level, when only your design of your circuit is present, because you need to do the test vector generation before your circuit is actually implemented, and then you will use these test vectors to test whether the circuit is functioning properly. Now let us look at the another method of doing fault simulation. Typically this method, though it is a closed method in the sense that you can actually find all the faults in one go, you do not have to perform multiple passes over the circuit, unlike, but still because of the complexity of the process, okay, it is not the direct simulation method, there is a certain evaluation is done. Typically this is not the one that is used, but it gives you a certain understanding of how fault simulation can be done, and so we do that. At each of the primary inputs we generate the list of faults that can be detected by the test vector. That is fairly simple. At a primary input, the fault that can be detected by the test vector is nothing but if you have the test, that particular vector has a particular input to be 0, the fault that can be detected is stuck at 1. If that there is possibly that can be detected, and if that particular input is 1, the only fault that can be detected is stuck at 0. Because if the true value and the faulty value are the same, that particular test vector is useless to detect that fault. Okay. So at each of the primary inputs generate the list of faults that can be detected by the test vector. Use this list to generate the list at other nodes by appropriate operations on these lists, and I will explain to you, take this example and explain to you how this works. We will not go into the proof of why it works, but it's heuristically, intuitively it should be possible to see that this is how the faults are propagated across the various gates. Okay, word length of the machine comes into the play, that number of faults that you can evaluate, let us say an AND of, you can only evaluate, so you are talking of word of a machine. So if it is 32 bits, so then 32 bit OR you can perform in just one instruction. If you say a register R1 or register R2, so you are not performing 1 bit of R1 with 1 bit of R2. So you are doing a logical operation in parallel on all the bits. That is how the ALUs are organized, that is how the processors are organized. They do a bit by bit AND or bit by bit OR. Okay. So the number of faults that you can simulate at one time is determined by the number of bits that you have in the word. If you have 16 bits, then you can do up to 16. Of course, if you are doing one fault free evaluation each time, then you can do 15 faults plus one fault free evaluation.
So but this is the word length of the testing?
Word length of the host machine, whichever machine the simulator is running.
So this example, the host machine was gates?
No. Please. See, this is all, whatever we are doing design and simulation on some computer. Okay, is assume that all this we are talking of large. See, I am now showing it manually, but everything is there are going to be programs which are going to do this test pattern generation. So obviously any program has to run on some host machine. Okay, so there will be a software program which will actually be performing the simulation. It will be running on some machine. So whatever is the base machine on which you are running, that will have a word length. And I can do my simulation in such a manner that I can fit so many faults in one evaluation of it. Because when you are considering a very large circuit, let's say it has 100,000 gates and you are performing this simulation, then you don't want to perform, and let's say corresponding to that so many faults are there, you have to limit the number of times you need to perform that evaluation. It's going to be time consuming to perform. And that's the reason it's called parallel fault simulation. I am in parallel simulating for number of faults. A number of faults I can simulate is restricted by the word length of the machine. Okay. So is that point clear? So now let's get into the next one. So this is the deductive fault simulation. In this as I mentioned, so from the example it will be clear that how this works. So I will take couple of examples here because there are some points that needs to be made. I am again taking the same, let me just hide this part for a moment. I am taking the same example and I have the same input test vector. So I have marked this test vector over here 0 1 0 1 0 and I have found the true values over here. I start with what is the list of faults that I can detect at A, at B, at C, at D, at E. These are possibly, this is not the list of faults that I can actually detect with this test vector. This is the possibility that at any, see, for example, if you consider any node, it has a true value. The only faults that can be detected with that particular test vector are the fault which corresponds to the opposite of that. If the true value is 1, you can only detect stuck at 0. If the true value is 0, you can only detect stuck at 1. So if you have n nodes, 2n faults, with any test vector a maximum number of faults you can detect is only n, okay, because you cannot detect the other n faults, stuck at faults which give the true value. Now LA is A1, LB is B0, LC is C1, LD is D0, LE is E1. What it shows is that list of faults that I can possibly detect with this test vector, and this I can find out using the test vector itself. Okay. Now I perform a successive evaluation. The method of evaluation is like this. Each AND gate you have to find the intersection of the lists at the inputs, and at each OR gate you have to find the union of the faults at the input, except with one major thing that you have to remember. If the true value of a signal is 1, then I have to use the complement of the list. Okay, this complement of the list, when I say LA complement, there is a meaning to it. What it means is, this is the total number of faults. Let's say this is the whole set of faults, and this is the list of faults LA. LA complement is the complement of this set from the universal set. That means it's all these faults. Okay, but this LA complement you actually never needs to evaluate, as we will see later on as the process goes. It's not that this is only a notional thing, that all the faults that are not covered by LA are covered by LA complement. Okay, but as we go and perform this evaluation, we will see that how it works. So when I use the, let us say at each node I talk of two sets. One is the faults that can be detected, but out of the faults that can be detected at that particular node, there are some faults which are propagated from the inputs and some faults which are generated at that node. If I consider this F may be able to detect some faults that are coming from the inputs, and F can detect some fault which gets generated at F. We know the fault that gets generated at F that can be detected. That is F stuck at 1. Because the true value is 0, the fault that can be detected which gets generated at F is stuck at 1. But I don't know which are the faults which come from B or C can be detected, and that's what I find using LF propagate. So LF propagate, when I write in this manner. See, I think some of you may not be able to see what is written here, so that's why I am writing again. So if I consider LF propagate, the faults that can be propagated, I had to take the intersection of the faults here and here, but for the true value which is 1, I will take complement intersection LC. Okay, now let me explain how it works. The faults that are the list of faults that are there, complement LC. So this one, as I said, LB complement is nothing but all faults which are not there in LB, and when I take intersection with LC, this is going to be nothing but LC, and LC was C1. So the faults that are propagated are C1, and you can see that this is how it works, because let us say why the fault on B is not getting propagated. If B fault was B0, if B0 occurs, this output would not have changed. Output still would have been, F would still have been 0 only even if B was stuck at 0. So this fault is not getting propagated. The only fault that gets propagated is if C stuck at 1, if this fault actually occurs, then output value is different, and this is what it evaluates. So LF propagate I get, and then I get LF. LF is nothing but what is propagated plus what gets generated here, and in this case is C1 F1. So these are the list of faults that can be possibly be detected at node F. Some of the faults which get propagated and some fault which gets generated over here. Now let us look at the next case, which is LGP. Faults that are propagated over here. LGP is nothing but LD complement union LE complement LE. It's a NOR gate. OR is a union function, NOR is a union and complement of that. You basically have to just replace your OR, and but you have to be careful about writing these lists, because if the true value is 1, I have to write the list as complement. If the true value is 0, I have to write the list as the same. So I have LD. So this one is nothing but, if you so you can actually write LD complement union LE to be nothing but LD intersection LE complement, and that is nothing but LD. I never have to evaluate this. Please remember that this is only comes as a, you have to just remember this, that this is the complement of all of that, but it would never be evaluated. So I have this LGP that is propagated is LD, and I can again check what is happening over here. If this D, what is the fault at D? Is D stuck at 0. If D stuck at 0 appears, both of them is going to become 0, and this G is going to be 1, and I can detect that fault. But E, if E is stuck at 1, if it is 1, 1 and 1 is still going to give me a 0, and I am not able to propagate the fault through this particular gate. And so I will get LD, and LD was nothing but D0, and my LG will be faults which come from D and the fault which get generated at G. The fault that gets generated as G is G1. I continue with this. I go to LH. Now this is a NAND gate, but please remember one thing, the true value of the output is 1. So I have to write this equation as LHP complement LF. Okay, I have to So I will write LHP complement because this is true value is 1, and I will write LF intersection LG complement. Intersection comes from the AND gate, complement comes from the NAND gate. LF and LG, the true value are both 0, so that's why I don't take the complement. True value of this is, so this is nothing but, if I can write this as LHP is nothing but LF intersection LG, and LF intersection LG is a set of faults which are present in propagated on F, which are detected on F to detected on G, and this is null. So the faults that get propagated through H is null. So no fault gets propagated through H, and so but LH, of course, the fault that get generated at H can be detected, and that will be HC, because H can get stuck at 1. If H is stuck at 0, I can detect that. I do now the same thing for this OR gate. I perform this evaluation. LIP complement, what gets?
How LF intersection LG is
LHP complement, LF intersection LG complement.
how is it null?
How it is null? LF and LG, you can see, is there any common element? LF was C1 F1 and LG was D0 G1. So the reason these two sets have no intersection, so that is null. And you can also see this, of course this is only for understanding this, that if any of these, you see what are these faults? The faults that are being detected at F or G, what are they going to do? Please remember, we are talking of faults occurring individually. All this analysis is based on only one fault at a time. Okay, though I am maintaining lists, but it doesn't mean that they are occurring simultaneously. So a fault at F is going to make this 1, a fault at G is going to make this 1, and if any of the faults occur, let's say if F becomes 1, it is not going to change my output, or if G becomes 1, it is not going to change my output. So the faults that have come up to here are going to be dropped by this gate is not going to propagate this fault further, because this node does not change if any of the inputs change. So that's clear that this node doesn't change, and because of that reason any fault that comes on F doesn't go here, any fault that comes on G doesn't go here, and that's what this intersection does. Okay, and now
Sir, how do we get the value of LF earlier?
same LF I got from the value of LB complement LC, LB complement intersection LC, from these two. This is how I generated. I first generated this list. This list I can get from my test input vector itself, basically opposite of what the input vector value is. If A is 0, I can only detect A1, B is 0, I can only detect B0, B is 1, I can detect B0, C is 0, I can detect C1, and so on. This list I got for the inputs I got from the test vector. I am doing all of this for this particular test vector. Once I have from the test vector, I have to blindly actually, this only of course I am explaining to you, but basically you can replace each of these gates by the operations, union and intersection. If it is an OR gate, union, complement, except that when you take the list, you have to take the true value of the list, and you have to use either the complemented list or the list itself. Okay. So for example, in case of propagated through F, I am taking LB complement LC, because B has a true value of 1 and this has a true value of 0. Let me now do the same thing for I. I is LIP complement, true value is 1, fault free value is 1. So I will take this, it is an OR, LA is 0, this is 1, so it is LA union LH complement. And I can take the complement of both, so this will give me, if I take the complement of this, so this I can replace it by LA complement intersection LH, fairly simple set theory. Okay, you can also think in terms of the De Morgan's laws that you have studied for logic, or you can also think in terms of the set theory that you have studied in schools. So it's basically just replace the union by intersection and take the complement. So now I have LA complement intersection LH, and this is LH. So that is LH was nothing but H0, and I can also detect the fault which gets generated at I itself. So Li would be H0 I0. And you can again see that A is getting dropped. If A is actually, there is a fault at A, the only fault at A which could have been detected was A1. This is directly is the primary input, and A1 is not going to make a difference at the output. So what this union and intersection and what we are doing captures essentially the propagation of the faults. How the faults are propagated across these gates, that is how these unions and intersections are capturing. And so by replacing this circuit by this and making one single evaluation, you see the basic difference is I need to do, unlike in case of the parallel, here also we are given a test vector and I am generating the set of faults. But in parallel fault simulation I have to keep on evaluating the circuit number of times because I can only evaluate one time. Here of course I have to maintain more complex structures because this list could be very long. Assume few thousand gates, the list could be that you need to maintain, it could be very long. And then you have to perform the set operations on these lists. That also takes time. But once you do that, given a certain test vector, I can actually get my, at the end of it, I can get the list of faults that this particular test vector can generate, and this is the complete list of faults that it can generate. So I have another example over here. I will quickly go through. It's basically the same example. In this I have just taken a different test vector, and I will show you where the differences come. Previously I had a test vector which was 0 1 0 1 0. Here I have taken a test vector which is 0 1 1 1 0. So because this C has become 1, of course this will not change, this will not change, this will change, because now I can, the fault I can detect is C stuck at 0 rather than C stuck at 1. These are same. So only change comes over here. But because of this change, wherever this participates in the whole path, there will be a change. And also the true value is changing. So the equations are, so when you look at LFP complement now, LFP complement is LB complement intersection LC complement. The true values are all 1 and that is 5. And evaluation of this LFP complement LB complement intersection LC complement is nothing but LFP is LB union LC. Take the complement of both sides and that. And implication is the faults that I can detect is both. So this is nothing but B0 C0. B0 was the fault at B that was coming on C0. Now what you can see that what's happening. If any of these inputs are going to go to 0, my output will change, and I can propagate these faults through this particular gate. Okay. So that is a possibility that, and similarly I then proceed ahead and do rest of the evaluation exactly the same as what we did, and finally I will end up with some set of, so by making the 0 1 1 1 0, now I can detect D0, G1, H0, I0. These are the faults that I can detect. So one of the primary input faults D0, G1, H0 and I0. I cannot detect faults at other faults that are there. So 4 faults can be detected. So if you are really comparing test vectors, so the way, as I said, the overall problem remains, what we are really interested in identifying a small set of test vectors which can detect a large number of faults. So if I am really to compare this test vector with the other test vector, I am better off with this because this can detect 4 faults that could only detect 2 faults. I have to of course consider other test vectors, and I have to consider test vectors which are sort of complementary in the sense that it detects faults which are not detected by, because you are going to include some test vectors in your test pattern, and those test vectors which do not you detect faults, they may be detecting fewer number of faults, but they detect faults which are not included by the test vectors are preferable, so that I can build basically a set of such test vectors. So when I did fault simulation or when I did deductive fault simulation, in both cases, please remember one thing, that I worked at the gate level. Typically most fault simulators work at gate level, but increasingly because of the fact that the circuit complexity is increasing, people are also looking at doing these simulations at higher levels. There is really no problem in doing simulations at higher levels, because what you really need to do in the first case, in the parallel fault simulation cases, you essentially have to write the function. Two things happen. What is the basics of doing this parallel fault simulation? The basis is this equation. I can write this f as an equation of these two inputs. If I can write this some particular node to be some other complex equation of some other inputs, I can still do the parallel fault simulation. A complex Boolean equation which represents, it could be some type of a gate or some type of a multiplexer. Still, if I can write my multiplexer to be, let's say a 2 to 1 multiplexer, I can write the output to be a function of the 3 inputs, the 2 data inputs and the select input. I can still do this. But when you go for such complex fault simulation with complex modules, please remember the faults which are generated within the node. What I said was, you take a 2 to 1 multiplexer. Why do I have to consider a gate? I can consider this C is nothing but A S complement plus B S. This is a Boolean equation that I have on C. So I can consider this to be a node, this output to be a node, and these to be inputs, and I don't have to consider all the gates that are there present inside. And I can do my parallel fault simulation with models like this. There is no difference at all whether I do, except that the gate that was present over here, now these nodes faults are not appearing explicitly. The nodes that are present within this, because at a gate level these nodes also will consider them for fault. Now here how do I consider, because I am not even considering them to be the nodes. But in some cases again, if we make an assumption that some of these nodes will, faults at these nodes will reflect at faults at some other nodes, which will typically happen very often, and some test vector will be there to actually include that fault, then these faults will also be detected. Of course it is only not explicitly but it may happen because of the nature of the test vectors that you have and nature of the faults that you have, that they may reflect in some other. Because if let us say this is actually stuck at 1, this particular node is stuck at 1, and I am actually testing, my test vector essentially sensitizes this path, because each of the test vectors is essentially going to sensitize the path. We will talk about that later in detail when we talk of path sensitization. But and the input I am transmitting from here is 0. I sensitize this path and I am transmitting zeros, but I get a 1 here, so this will appear that this is stuck at 1. Though the node that was stuck at 1 was somewhat in between, but this may appear as stuck at 1, and my fault, I may be able to find this fault. So it is possible to do that, but my actual fault coverage will obviously go down, but the number of test vectors that I will require will also drastically come down, because I have fewer nodes now to bother about. And this particular approach is, you can apply not only to fault simulation, you can also apply to deductive fault simulation, because as long as I can formulate those equations, the equations were this union, intersection and complement, if I can understand how these faults are getting propagated, and I can, and those equations are very simple to formulate in that case, because you basically, if this is your multiplexer, this is my multiplexer, I write the equation for this, I write the equation for this, I write the equation in terms of these equations, and I get the equation for how the fault gets propagated. So I can write those list equations and I can again do that. But again, so I am not going to consider the faults that are going to occur in this. So both of these processes, there is a possibility of a level of abstraction higher than gate level, but typically most of the usage is at the gate level, but it is also possible to generate these test patterns and these test vectors considering circuits which are more complex.
So if we abstract at the higher level, won't there might be some errors which get get undetected.
Yes, yes, sure. The coverage is going to go down. There is no doubt about that, because what I am assuming is the faults that I am not even considering the fault at this. What happens is I am not explicitly going to test for this fault, but what I am assuming is many times, and this happens, that many times the faults at here will actually reflects that fault at some other place. If it happens and I have a test vector to cover that fault, it may get detected. But if I, if that doesn't happen, if faults tend to have an effect of cancellation or have an effect of, not getting propagated properly with my test vectors, because I have not explicitly chosen a test vector to get this fault, but it may just happen that some of the faults will be detected. So coverage actually goes down, but then you have to pay something. Okay, the advantage you get is lesser time for generation of the test patterns, which is of course a one-time effort. Generation of the test pattern is done even before, as I said, circuit is fabricated, and it's a one-time effort. It is not to be used each time for each copy of the circuit. You generate a set of test patterns and then test all the copies of the circuit. So that's a one-time design effort, but on the other hand, you also save on the number of test vectors, and that's also going to save on the time that you incur on testing itself, because as I mentioned to you, the test jigs are extremely expensive and you want to spend only as little time as possible on the test jig itself. We will stop here. We will consider the other problem now in the next class. Given a fault, how do I find out the test vectors, which will cover that.